All right, thanks, Eric. I think I might have rearranged my title since you last saw it, but it's still the same talk. So yeah, like you said, this is a talk about linear types, specifically in Scala, and the angle that I'm approaching this from is finding a way that this can be kind of practical in a work situation. So hopefully that's the message that we get across, but we'll give it a try. Cool. So before we get started, I want to briefly introduce the concept of linear types, what they are and what they're all about, and then we'll get into really get into the meat of it later. So basically, this is sort of the key takeaway framing this whole talk, is that linear types ensure that values are used exactly once, and really that's it. And so this can help us write code that is more understandable and has fewer bugs, as we'll see. We'll leave it there for now and get into it in a little bit. But first, I want to talk just about types in general. So again, the premise of this talk is that it is linear types, but really types in general, and that types are good because types are restrictive. So we have this Minsky quote that I really like, that types make illegal states unrepresentable. So things that we don't want to be able to put into code, we use types to restrict ourselves from doing. So for today, for this talk, the plan is to extend Scala's type system just a little bit to make it a little bit more restrictive. We don't want to make it too restrictive. We can really go overboard there until we end up with a theorem prover if we go all the way. And those aren't too practical. It's a little hard to write production code in something like that. So we'll just make a few new additional illegal states unrepresentable in Scala. Before we do that, though, I want to take a quick tour of types and specifically look at what increasingly strong types can really do for us. So we'll look at function signature with no types, with the types that most of us are used to. I call them normal types here. Generic types, higher kind of types, and then finally we'll start getting into linear types as an incremental evolution from there. And actually, sorry, one thing that I forgot to mention, there will be some interactivity later, but I highly encourage questions, and if you want to interrupt me, please do. It's welcome. I think Eric will let me know if there are any questions on any of the stream or Discord or any other sources that he's monitoring. So yeah, please keep those coming. I'm happy to address them as we go, because we're going to be looking at a lot of code and hopefully not too quickly. So let's start with our little progression of types in JavaScript. So with no static types at all, such as in JavaScript, we know very little about code by just looking at a function signature. So in this example, we have a function foo. It's got a couple of arguments, and we can't see its implementation. So we know almost nothing about this just from looking at the signature. We know that foo is a function, and well, that's about it. It looks like it takes a couple arguments, but because this is JavaScript, that's not necessarily the case. The body of this function could use undeclared arguments, because in JavaScript you have access to an array of all available arguments, whether or not they were passed.
Hey,
so we don't know if foo.
Oh, yep. Sorry to interrupt. So quick question for you. So are linear types like your invention, or what's their background in history?
Yeah, good question. No, they're definitely not my invention. They are they're just a theory from type theory, or they're, I guess, a topic from type theory that you can find in some other languages. Like Haskell has a proposal called Linear Haskell that introduces this incremental type system improvement. Really, they go back to the different kinds of type systems that do exist. And there are lots of different ones, and I am no expert on them. But the type system that most of us are used to, that we just consider normal, is actually called an affine type system. And a linear type system is similar, but it has different rules about how many times different values can be consumed. So, so this talk is basically taking that idea, which is very much not mine, and introducing it into Scala, which today does not have support for linear types. All right, so going back to this JavaScript code, we said we know that this is a function, and that's pretty much all we know. We don't know if foo takes any arguments. It looks like it does, but it might ignore them. We don't know the types of those arguments. Are they strings or numbers or something else? We don't know what foo returns, if anything, or what its type is. So the surface area for testing this function is enormous without knowing more about the implementation. And then for normal types, or sort of plain old types, if we just add some type annotations to this function, so now our arguments, x and y, are both integers, and our return type for foo is also an integer. Now we know a few more things about foo. We know that it's a function, and we know that it takes 2 arguments. This is now Scala, so it definitely takes exactly 2 arguments. Those arguments are both numbers, and foo returns a number as its result. That's about all we know. We don't know what, if anything, foo does with those arguments. It could do some math on them and return the result, or it could just return whatever number it feels like and ignore the arguments, or something in between. And we really don't know. If we make foo generic in the type of both its arguments and the return value, now we're starting to know quite a lot more about what foo could possibly be. So we see that foo takes 2 arguments, just as before. They're both type A, and type A is unknown, at least to the author of foo. So if I'm writing foo and this is the type, I really have no information about what x and y are, because I don't know what A will be at the time that it's used. And similarly, the return type is also this unknown type A. But that unknown kind of buys us something interesting, and that's that for foo to produce an A, for any arbitrary A, we don't know how to conjure up an A other than throwing an exception or returning null without using either X or Y. So with this signature, we can infer that foo probably just returns X or returns Y, or throws some exception or something like that. But we don't know which of these 2 arguments foo actually returns. So let's go one step further and use a higher kind of type. So now if we constrain A, which is our type variable, to have a monoid instance, then we know that, well, foo has access to a monoid for A, whatever A might be. X and Y are both A, just as before. Foo returns an A, just as before. So now we know that, just like before, foo could return X or could return Y. But since A has a monoid, foo could do some monoidal concatenation of X and Y, or Y and X, or X and X, or something like that. So the intent behind foo is starting to become more clear. We don't know for sure that it does some kind of concatenation of X and Y, although it probably does, because why else would the implicit be there? And so let's go one further step, and now we're going to be in linear types. So as I said before, linear types ensure that values are used exactly once. And so if we constrain foo's arguments to be linear, and the way we do that is with this marker interface, which comes from a project called Linear Scala, which we'll go over briefly. So if we annotate the argument types with this marker interface, we're saying that X and Y are both A, but they are linear, meaning X and Y both have to be consumed exactly one time in the body of the function foo. So that tells us that foo definitely uses both arguments. If foo just returned X, then we couldn't say Y is linear because Y was never used, and vice versa. So foo uses both arguments exactly once. A has a monoid. So really, there's only a couple of possible implementations of this function, and that is to use monoid to concatenate X with Y or Y with X and return that. So from this progression from no types all the way to linear types, the point is that types restrict what our code might be able to do, and they increase the space of what our code cannot do. And that really gives the reader a lot of information, increasingly more information as our types get more and more strong. And the reader, in this case, can be a person, it can be a developer maintaining this code, or it can be a compiler, as we'll see today, and gives that reader just additional information about their code. Okay, so let's go back to what linear types are. So I've said a couple of times, and I want to keep drilling this point, that for our purposes, linear types ensure that values are used exactly once. But what does used mean? What do I, in this context, what are we talking about? So let's look at an example. So here we have 3 little snippets of code, and the value x, so x is bound to the integer 0. And so you could call it a declaration or a reference, but it's never used, at least in the context of this talk. So we're never reading x and doing something with it. In the second snippet, we have y is set to 1, and we print it. And so in that case, we call y being used one time by that println statement. And then in our third block here, we said z equals 2, and then we print it twice. And so here we say that z is being used twice. So for our purposes, used really just means dereferenced. Every time we dereference a variable or a value or a binding or whatever it might be, we consider that a usage. And so this is a fairly simple definition of linear types. There are actually quite a few different definitions of linear types out there. For our purposes, our definition is most like what you can find on WikiWeb, which in particular says that the reference count of linear objects is always exactly 1. And that differs. So Linear Haskell, for example, is right now it's a proposal, I think, for extending the Haskell compiler. It's quite a bit more sophisticated, and it states that linearity is a property of function arrows rather than of types or references, like we're doing here.
But hey,
also,
sorry to interrupt you real quick, and this might be a little bit late of a question, but does one say that foo is linear in X and Y?
That I think in the Haskell definition, that is how you would say it. When we're just counting references, which is how linear Scala works, I'm not sure if that would be completely correct. I would definitely say that X and Y in the context of foo are linear.
X
but
and Y
foo itself, yeah, I think so. Thinking about it, I don't think I would say foo is linear. Let me just go back to that slide.
If you feel like you need to circle back to this in the Discord later.
Sure, yeah. I'll time box it at 10 seconds here. I think for me to say that foo is linear, I would want the return type to be linear. But then that gets into some weeds. We can actually call foo more than once, which isn't very useful, as we'll see with Haskell. So let me jump ahead. So back to Haskell. This is what linear types look like in Haskell. So they normally the type of a function would be A, right arrow, B, for a function that takes an A and returns a B. Linear Haskell, again, is this proposal to extend Haskell, and they introduced this lollipop operator, and that is called like a linear arrow. And so here we say that that F, so sorry, I'm trying to phrase this based on your question. So that F is a linear function. And so a key difference here that I'm sort of fumbling to say is that F itself can be used many, many times. It's not that F will only ever have one reference or one usage. It's that it's F applied to a specific argument. That combination is what needs to be linear. So for example, if I say F of foo and then F of bar, so I'm calling the F function and passing it 2 different arguments. F of foo would be linear, like that exact evaluation would be linear, and there would only be one instance of that. And then F of bar, again, there would be just one instance of that, and so that would be exactly one usage of 2 different things. Hopefully that makes a little bit of sense. We can take this offline afterward and really get into the weeds. And I'm very much not an expert in the Haskell implementation of linear types. Okay, so in the interest of time, I'm going to skip over a little bit of how these actually work in Scala. But in a nutshell, to implement linear types in Scala, I just used a custom linting rule in Scalafix and called the project Linear Scala. And really all it does is it traverses the syntax tree, looks for bindings and variables that have a linear marker interface, counts those, or keeps track of those, and then counts dereferences to them and makes sure that all those dereferences are equal 1. That's really all it does. So I'd be happy after the talk to dive into how that works, if anyone would be interested. But the important thing for this talk is what linear types can do for us rather than how this particular implementation was done. All right, so I have a few, oops. Sorry about that. Okay, so I have a few exercises here that we can go through until we run out of time, basically. So here's sort of a thought exercise. Can anyone spot the bug in this code? Well, since I can't see Discord right now, I'll answer myself. So we're passing the wrong arguments to the monode instance. So here we're creating a function called concat. Concat takes 2 arguments of type A, where A has a monoid, and it returns an argument of type A. So we're probably just delegating to the concat inside of the monode instance that is available for this function call.
Also, but in our implement is that X is used twice.
Yeah, exactly. So we're conjuring up our monoid, and we're calling concat, and then we're passing X twice. So yeah, that compiles just fine. That would run, but it's probably not what we meant to do. We probably meant to concat X and Y. So if we run this code, Z will be 1, 2, 3, 1, 2, 3 rather than 1, 2, 3, 4, 5, 6. So how can we catch this at compile time? That's really what we're going for with linear types. Well, we can make it linear. So with linear Scala, as I said, we can mark certain types with this linear marker interface. And then that requires that values of those types, in this case, X and Y, must be used exactly once. So everything else in this code is the same. We've just added these markers. So X is A with linear, Y is A with linear. We still have our bug here. And then I've just cast these 2 lists so that we'll keep the compiler happy. And then we try to concatenate X and Y, just like before. So when we try to compile this with linear Scala, we get a compile error. So the linter will give us a couple of errors. It will say that, hey, you told me that Y is linear, but you never used it. It was used 0 times, and it must be used once. And similarly, you told me that X is linear, but you're using it twice. And so these are the errors that you'll get from linear Scala when you try to compile this code. So now this bug is caught at compile time, and which is great. It's a much better time to catch bugs. So now we can fix it. We got the compile error. We fixed the code. We change our X to a Y here. And now, not only is it correct, but now the code will actually compile. Pretty simple example, but hopefully it illustrates that there are some categories of bugs that will make the compiler today happy that we can catch if we make the compiler a little bit more restrictive.
So I guess one question is, could you alias A with linear to something shorter in order to shorten the code?
Yep, yeah, there are lots of different ways that you can make something be linear. Here we're mixing in a trait. You could have a type alias that's like, L of A equals A with linear. That would work. You can make your own custom data types that extend linear, like case class foo extends linear.
And I was actually wondering, like, is there a way to to get rid of the as instance of stuff?
Probably. It's pretty annoying to have to write it, but I think that, so one possible improvement I think for linear Scala is rather than a marker interface, which causes all of this casting to be needed, when we use it, using an annotation or something that actually gets erased by the compiler and then never even makes it into the bytecode. could be a way to make the syntax a little bit cleaner. Linear Scala, as it's implemented today, is mostly a toy to experiment with linear types in Scala. So yeah, I definitely don't think that the syntax here is the cleanest, but it at least lets us demonstrate the idea.
Very cool. And I guess one more question, and I don't understand the question, but maybe you do, which is, does A with linear effectively cast A to an R value reference in C++ terms?
I have no idea.
Okay.
So what would be nice
I'm not
is
alone.
what would be nice is if making a type linear didn't actually change its type like we are here. So that's why I would love to erase it at compile time. Maybe make this a macro instead of a Scalafix rule. Scalafix just made this super easy to implement at the cost of we have to have this marker interface everywhere. Cool. So we have a bunch more of these examples and another 10 minutes to get through them. So I'd love to show just a few more cases where this can be useful. So once again, let's try to spot the bug. In this case, it's a more subtle example, and it might not even be a bug. We don't really know. But basically, we have x bound to two different values, right? We have x equals 6 up here and x equals 8 in the foo function. And then foo takes x and y and multiplies them and returns the result. So that's fine. There's not necessarily anything wrong with this. We do this all the time. It's just shadowing. But it could potentially be a code smell. It could be something fishy. Like, did the author really mean to use this x, or did they want 6 up here, or vice versa? Maybe they wanted 8, and the 6 up here is actually unneeded. It's unused by anything. But it's really unclear just looking at the code with no explanation of why there are two x's, which one should be used. So we can't assume that we can get rid of either one of them, but we can force the author to decide by making them linear. So let's do that. So once again, all we've done is change the type of x, and y to be, instead of int, it's just int with linear. And we're just doing that by casting. So by making these linear, we are telling the compiler, well, specifically telling Linear Scala that this x must be used exactly once, this x must be used exactly once, and this y must be used exactly once. And we can see just from the code available that that's true for these two values, but this one is never used. And sure enough, if we try to compile it, we get a compile error that says, this is linear, but you never used it anywhere. And so to fix it, well, at the risk of breaking the code and changing its meaning, we need to get rid of one of the x's. So I'll assume that the author actually wanted to use this global x and drop the one inside the foo. Really, we would, at this point, if this were production code, I would want to go back and figure out what is the use case, what is this code actually trying to do, and then maybe eliminate this one or change some value names or try to figure out, well, was this x actually supposed to be used somewhere else, or is it just essentially dead code? Any of these is possible. We don't really know for sure, and linear types can't tell us. What they can tell us is that something is a little bit off about this code. And now that we've removed one of those x's, the intent is much more clear. In the interest of time, I'll go through this one really quickly. This is the exact same example, except rather than a method, we're using bindings in a for comprehension. So we've got x, y, x. There are two x's. One is bound to 6, one is bound to 8, and the second one shadows the first. So when we return x times y, we're multiplying 8 by 7. So again, the reader of this code could say, well, wait a minute, what's the point of this one? It's not being used. Can we get rid of it? Well, if we make it linear, the compiler will force us to. So if we change our types to be option of int with linear, now x, y, and x must each be used exactly once, and our compiler tells us so. And so we can fix it by getting rid of the unused x. And so I'm getting rid of the one that's 8, again, just like I did before. So again, potentially changing the meaning of this code. So I may have actually just introduced a bug by changing this x to be 6 instead of 8. So the next step would be to go and find out, how's this code actually supposed to work, and make sure it does that. But at least once we're at that point, we can't accidentally reintroduce the same sort of shadowing potential bug. Okay, and I think this will be the last example that we go through at the code level. So again, let's try to spot the bug here. We have a function that takes a source and reads its contents and returns the contents as a string, and then closes the source, whatever it might be. Then we read a file as a source, and we read its contents and print it to the screen twice. And as you may guess, we have a problem here. So this code compiles just fine. But if we try to run it, we get a runtime exception on this line because when we pass s into read the second time, s has already been closed. And so s.makestring will throw an exception about the stream being closed. So in other words, we're trying to do something with a file whose handle has already been closed. And you can imagine this pattern applied to really anything that's closable, network connections, database transactions, what else? Basically any kind of I/O, really, anything with a closable interface. So once again, let's make this linear. All we've changed here is we've made s itself linear. So I'll go back one. Before s was just a source, and now s is a source with linear, and we just do that by casting. So now when we try to compile this code, we get compile errors because linear Scala tells us that, hey, you told me s was supposed to be linear, but I see you're using it 2 times. So we actually get 2 separate errors on this code. And so to fix it, we just need to make sure that we're only using s 1 time, we're caching that result, and then that's what we're printing out twice. There are lots of other interesting use cases that we don't have time to get into, and also are a little bit hard to show in a slide format. But some of those include making sure that a database query is not run after the underlying connection or transaction has been committed or rolled back. That's a bug that I've run into before. Making sure that a stream of data is fully consumed, whether we're pushing or pulling a stream, or that some kind of protocol is adhered to. This happens before that, before doing this and then the other. We could use linear types to debounce code that has side effects or that is non-idempotent but needs to be idempotent. And then actually, as we saw, we can detect and prevent dead code. So if there's a variable that's just sitting around unused, that might be important to know because either it should be used somewhere and there's a bug, or it doesn't need to be used and we can delete it and we don't have to maintain it. There are lots more examples like this in the Linear Scala project. So if you dive into this directory, which is essentially the tests, you can see a bunch of examples. All right, so the point of all of this is that linear types are an incremental increase to the restrictiveness of our type system that ensures that values are used exactly once, and that this is a technique that can help us write code that is more understandable and has fewer bugs. And that's it.
So there's no questions in the Discord, but I actually have a question, which is, were you able to implement this entirely within the scope of a library, or did you need to write any plugins to get this working?
So I built this entirely on top of Scalafix, which is a plugin that lets you write linting rules. So you can write any kind of custom linting rules, and those rules have access at compile time to basically the full AST of your code. And so it kind of sets up all of the underlying infrastructure for me, the author of this rule, to traverse that syntax tree and look at anything I need to look at. So yeah, this would need to be either a compiler plugin or a macro or an SVT plugin or something like that, so that we can do this sort of meta analysis of the code itself.
Yeah, I was just thinking that, where it's like, if I wanted to write this, I think I would need to write a compiler plugin. So, but it sounds like it depends on Scalafix.
Right.
Right on. Well, then that's all the questions, and we're good on time. So, all right. So thank you very much for coming in to talk to us about this, James. I really appreciate it, and this has been really interesting for me and for others as well, I'm sure. I'm really curious to see like where all this goes and what the future of the linear types is.
Cool. Yeah, and if you take a look at these slides, I'll post a link later in Discord. There's a whole bunch of further reading, and the Linear Haskell paper and talk that Simon Peyton-Jones gave is really fascinating and easy to follow, actually. And then you can also learn about linear types is just one example of a substructural type system, and the Wikipedia page on that is pretty helpful. We also touched a little bit on theorems for free when I talked about, at the beginning, the progression of types and what types tell us about what the code can or cannot do. So I'd recommend that paper for sure. And then linear Scala itself is probably more useful as an example of how to write a Scalafix rule than how to implement linear types. But it's worth browsing around if you're curious.
Would you mind, if you could, maybe posting those in the Discord room?
Yep, we'll do.
Awesome. Cool. Well, thank you so much again for coming and sharing this with us.
All right. Thank you.